Chapter 4 is divided up into 3 different lectures. It is going to be talking about compounds and their bonds. So if you remember from previous lecture, a compound is 2 or more different elements that are bonded together with a fixed ratio. Okay? This chapter is going to focus on 2 different types of compounds, either ionic compounds or covalent compounds. This particular one, part A, is going to focus on ionic compounds. So going back to the flow chart that we had talked about in the previous lectures, matter is divided up into 2 different categories, either mixtures or pure substances. Before we had talked about how mixtures are divided up further into either homogeneous mixtures or heterogeneous mixtures. But we're going to focus on compounds today, which are pure substances. So remember that pure substances are broken up into either an element or a compound. And this is where our flow chart had stopped previously, but we're going to take it one step further today and talk about how compounds are either broken up into ionic compounds or molecular compounds. Another word for molecular compound is covalent compounds. So we'll talk about that more in part B of the videos. So just while I've got this slide up here, a little bit more about ionic compounds. They're held together by ionic bonds. They are usually between a metal and a non-metal. So remember from your periodic table, you locate your metals because they're to the left of the stair step, and the nonmetals are to the right side of the stair step. Going to this side of the flow chart, the molecular compounds or covalent compounds are held together by covalent bonds, and they are usually a nonmetal bonded to another nonmetal. So we're going to talk about these when we get to part B. The next video, we're going to focus this video on the ionic compounds. So inert gases, which are also called the noble gases. So that's what I had asked you to memorize. That's your 8A family, are called the noble gases. These gases are chemically unreactive. So you find them in nature not bonded to any other element. There are, a few exceptions. We have found some argon and krypton compounds, but for the most part, these elements are content. They don't tend to bond to a lot of things. So there's something special about the noble gases, which is why they get the word noble. It turns out that all the gases with the exception of helium, have an octet of valence electrons. Now octet means 8. So if you look at the electron dot structure, for neon, argon, and krypton, remember when you're doing the electron dot structures, you just put down the valence electrons. And remember, you get the valence electron from the group number. Well, the group number for the noble gases is the 8A family. So all of the noble gases have 8 valence electrons, with the exception of helium. Helium only has 2 valence electrons. Okay, so that is worth knowing. So there is something special in nature about having an octet of valence electrons. So having an octet of valence electrons imparts a stability and is the basis of what we call the octet rule. So the octet rule is defined as during the course of a chemical change, atoms are either going to gain, lose, or share electrons to obtain an octet of valence electrons. So I'm going to go back to that slide. So focusing on ionic compounds, it's going to be showing how the atoms are going to gain and lose electrons in order to achieve their octet. When we switch gears and we start talking about molecular compounds, then the atoms are going to start sharing electrons in order to achieve their octet. Okay, ionic bonding. So a couple things about metals. Metals will lose electrons during a chemical change as they react to obtain an octet of valence electrons. So you'll want to have that memorized. Metals lose electrons. They are going to form ions with a positive charge, and here is a new vocab word because I have it underlined. An atom that has a positive charge is called a cation. Metals would rather lose than gain electrons because metals have a low ionization energy. So if you remember at the end of one of the previous lectures, we talked about the trend on the periodic table and how you know that the atom size decreases as you move from left to right and bottom to top. And then we talked about the ionization energy, which is how much energy it takes to pull an electron off. And I wanted you to know the trend there, that ionization energy increases as you move from left to right and bottom to top. Okay? So Metals have a low ionization energy, so it doesn't take much energy to take an electron away from the metals. So that's why they tend to lose electrons and become positively charged. Nonmetals, on the other hand, are going to gain electrons during a chemical change as they react to get their octet. Nonmetals form ions with a negative charge, which I want you to have memorized. It's called anions. If you look at these two words, when I was a student and I had to memorize this, I remember thinking to myself, well, cations, the T looks like a plus sign to me. So I had memorized cations were the positive ions because of the T looking like a plus sign. I've heard other teachers say, to help students remember this, is that cats have paws. So they're little paws. So cations then are positive. So if that helps. And then I don't have a cute one for anions, so if cations are positive, then anions by default must be negative. Nonmetals would rather gain electrons than lose them because they have a high ionization energy. Okay? It takes a lot of energy to steal an electron away from a nonmetal. So they don't tend to form cations. They tend to form anions, where they gain electrons. So here's a picture of sodium chloride reacting, or sodium and chlorine reacting to make sodium chloride. Okay, so I start off here with a picture of sodium atom, a neutral sodium atom, where it has 11 protons and 11 electrons. And this is a kind of a general electron structure, because we know that if I asked you to do the electron configuration for sodium, we would have the first 2 electrons being in the 1s, and then the next 2 being in the 2s, and then the next 6 being in the 2p. But in this picture, I'm showing all the electrons. I'm only showing the shells. I'm not showing any sublevels or subshells. So in the first energy level, there's 2 electrons. In the second energy level, we have 8 electrons. And then since sodium has 11 electrons, that last electron goes in the third energy level. Well, we said that metals will lose electrons to achieve their octet. So what happens is the sodium will lose this outside electron. And if we look at chlorine atom, chlorine has 17 protons, and I'm showing there's 2 electrons in the first energy level, 8 electrons in the second energy level, and there's 7 electrons in the outermost energy level. Now, remember the definition of valence electrons. Valence electrons are the electrons in your outermost shell. And we determine the valence electrons by looking at the group number. So if you found chlorine on the periodic table, it would be in the group 7A, meaning it has 7 valence electrons. Well, sure enough, here's a picture showing those 7 valence electrons. Well, chlorine wants to have an octet. It wants 8. And sodium here wants to have an octet. Well, if chlorine steals this electron from sodium, we end up getting these ions. So sodium, since it lost an electron, becomes positively charged. Now, that's hard for a lot of students because they think about math and they think, losing is subtracting, so you're going to have a negative charge there. And over here with the chlorine, since it gained an electron, a lot of students will think of that as addition, and they want to make this a plus sign. So don't do that. Think about the fact that electrons have a negative charge. So when this sodium atom loses this negatively charged particle, it ends up becoming a positive charge. And the chlorine, when it gains a negative particle, is going to end up having a -1 charge. Okay, so you want to kind of keep that straight. When a metal loses electrons, it becomes a cation. When a non-metal gains an electron, it becomes an anion, negatively charged particle. Okay, that also works if you think about, summing up your protons and your neutrons. In a neutral atom, the number of protons equals the number of electrons. But when we move down to the sodium ion, I have 11 protons, but I only now have 10 electrons because it lost one. So 11 protons, positively charged particles, and only 10 electrons is going to give us a net balance of a +1 charge. So you want to be able to do that. So this would be an ionic, forming the ions. The metals become cations, nonmetals become anions. So an ionic bond is one formed by the transfer of electrons to produce ions of opposite charge, which then attract each other. Because remember, we talked about opposites attract. Positively charged particle is going to want to hang out with a negatively charged particle. Atoms in ionic compounds, which are usually metals bonded to a nonmetal, are held together by what we call an ionic bond. So here's a picture of some ionic crystals here. And if you look, It's kind of deceiving. Let me grab my pen here. Pointer. When we write the formula for ionic compounds, like for example sodium chloride, you may think that this is the table salt. Since the formula is 1 sodium to 1 chlorine, you might think that that's actually what you have. But when you have an ionic compound, these cations and anions build up into what we call a crystal lattice, where you can grow crystals of ionic compounds. So here's a picture of sodium chloride where we've got, surrounding every cation is a bunch of anions, and following every anion is a bunch of cations. So it just so happens for sodium chloride that the ratio that there is, if you reduce the amount of sodium chlorides, it's a 1-to-1 ratio of sodiums to chlorines. So here's a learning check. Part A says the number of valence electrons for aluminum is. So remember, we determine the number of valence electrons by looking at the group number. Well, aluminum is in group 3A. So it has 3 valence electrons. If you want, you can pause this video and try this learning check by yourself and then come back and see how you did. B says, what is the change in electrons for an octet? So remember, your metals are going to lose their valence electrons. Okay? So since aluminum has 3 valence electrons, it is going to lose those 3 electrons. So we're going to circle number 1. It's going to lose those 3 valence electrons, and then it'll have an octet because there will be 8 electrons in the lower energy level. Part C says the ionic charge on aluminum is. So here's where a lot of students mess up. It lost 3 electrons. So a lot of students want to do the whole 3 minus because it lost the electrons, but that's not true. If it loses 3 electrons, then it has 3 protons that now no longer are balanced out by those 3 electrons it lost. So you're left with 3 positive. You might just want to, if that's hard for you to see, you might just want to get it memorized that metals lose electrons and then they become cations, which are positive. So that'll kind of help you remember that since aluminum is a metal, it's going to have a 3+. So then the symbol for the aluminum ion is going to be, since it has a 3+, it's going to be number 1 here, the aluminum with the 3+. Okay. So we always put the charge of the ion in the upper right-hand corner. Here's another learning check. The number of valence electrons for sulfur is. So you get out your periodic table, you look at the group number, and it'll tell you the group number for sulfur is in 6A, so that means it has 6 valence electrons. The change in electrons for an octet to be reached. Well, sulfur is to the right of the stair step, so we know it's a nonmetal. And nonmetals are going to gain electrons to reach their octet. So if it has 6 valence electrons right now, how many electrons does it need to get to 8? And the answer to that would be 2, so it's going to gain 2 electrons. So the correct answer is number 2 there. And then the ionic charge on sulfur is going to be a 2- since it gained 2 electrons, and electrons are negative. Something to note about writing the charge: when you're writing the ionic symbol, you write the number before the charge. Now, I'm not personally really picky on that. If I'm grading something of yours and you have a +2 instead of 2+, that's going to be fine with me. But for the purpose of your homework and doing it online, the software is very picky about you putting the number before the charge. Also, another thing about the software, let me grab my pen. Like, for example, going back to the sodium, I would have no problem if you said sodium loses 1 electron, so it has a 1+. I also wouldn't mind if you put the plus before the 1. That doesn't bother me. But what a chemist usually does is they tend to leave the 1 off. So they tend to do a +1, or in the case of the chloride ion, a -1. Okay? So on lab reports and things like that, or exams, I don't mind if you put the 1 in there. But when you're doing the homework online, it's picky that you just put the plus or the minus if your charge is a +1 or a -1. Okay, so there's ions. Let's talk a little bit about ionic compounds. They consist of positive and negative ions. They have attractions that we call ionic bonds between the positive and negative charged particles, which are the cation and the anion. They have high melting and high boiling points. So that's a point to kind of memorize about your ionic compounds. And they tend to be solids at room temperature. I found when I was a student, I memorized that sodium chloride was an ionic compound, and then when I was asked questions about the properties of ionic compounds, I tended to just kind of think about sodium chloride. Now, you probably haven't had much experience trying to melt sodium chloride, but it has a very high melting point. A lot of students get that confused with dissolving because it dissolves readily in water, so they think, oh, it's melting, but it's not. Okay, so if you just took sodium chloride and you tried to just melt it without any water to turn it into molten sodium chloride, you'd have to add quite a bit of heat. So ionic compounds have a high melting point, high boiling points, and they're solids at room temperature. So sodium chloride, I think we're all familiar with, is solid at room temperature. Ionic compounds are electrically neutral, meaning the amount of positive charge you have has to exactly equal the amount of negative charge. Because once those cations and anions come together, the amount of positive and negative charge is going to balance each other out. So to determine the formula of ionic compounds, there's this trick, which we call the crossing method or the crossing shortcut. So I'm going to show you that trick. I know your book goes into something called balance of charge, and you're more than welcome to do it that way. But I'm going to go ahead and stick with the crossing method when I teach this class. So using the crossing shortcut to convert the charges to a formula, what you're going to do is you're going to take the charge of the cation and make it the subscript of the anion, and then you're going to take the charge of the anion and make it the subscript of the cation. And then here's the step that a lot of students forget, so don't miss this very last sentence. You're going to reduce to the simplest ratio if it can be reduced. So if your subscripts can be reduced to a lower ratio, you'll want to do that. So here's a picture showing this. So when you go to write your ionic formulas, I recommend that you always take the time to write your ions first. Okay, that's where a lot of students make mistakes. They want to go directly from the name to the formula. And I'm really going to stress, take the time to write your cation and your anion, because then you're set up to do this crossing method. Something to notice is you're just bringing down the number. You ignore the charge. Don't bring the plus or the negative down. So since magnesium is a 2 plus, that 2 is going to become the subscript over here for the nitrogen. And the nitrogen becomes a 3 minus, and so that 3 becomes the subscript for magnesium. So that's where we get the 3 for magnesium and the 2 for the nitrogen. Okay, so that's how we're going to do our formulas for ionic compounds anyway. So here's an example. What is the formula of the compound formed between aluminum and the oxide ion? So we're going to take the 3 here, and it is going to become the subscript of my oxygen. And the 2 superscript on the oxygen is going to become the subscript on my aluminum. So we end up with, get my marker to work, Al, and then I bring the 2 down. And then the oxygen, how many oxygens do I need? So I look at aluminum's charge and I bring the 3 down. And then the last step that I don't want to forget is, can 2 and 3 be reduced any lower? And the answer is no. So there is my final answer. If I have magnesium 2 plus and the sulfide ion with the 2 minus, and I do my crossing method, so the 2 comes down on both of these guys. So I get Mg2S2. So there's the crossing shortcut. My last step is, can it reduce? Yes, 2 and 2 can reduce down to 1 and 1. So the true answer is going to be just 1 to 1. So that is magnesium sulfide's formula. Okay, so here's a learning check, one for you to do on your own. Select the correct formula for each of the following compounds. So if we do the crossing method, I am going to need a formula that has 2 sodiums, and this invisible one, when it becomes a subscript, stays invisible. So I'm looking for a formula with 2 sodiums and only 1 sulfur, and that would be number 2. If I do B, the 3's are going to come down, but what happens to the 3's? I get a lot of students who pick number 3 to be the correct answer, but you'll get it wrong if you pick this answer, because the 3's can reduce down to 1. So the correct answer is actually number 2. For C, I am looking for 3 magnesiums and 2 nitrogens, so that would be number 3. Okay, the charge on the representative elements. Now remember, the representative elements are the elements that have an A after the number in their group number. It turns out that the charge on the representative elements equals the group number if it is one of these cations. So in your group 1A, all of the metals plus hydrogen make a 1 plus charge. The 2A metals make a 2 plus charge. Over here, when we get to the nonmetals, now you kind of want to think through, nonmetals are going to gain electrons. How many electrons does it need to gain to reach its octet? Well, if we look at the 7A family, they have 7 valence electrons. So to reach their octet, they just need 1 electron. So that's why all of them have a -1 charge. The nonmetals in group 6A need 2 electrons to reach their octet. That's why they have 2 minus. And then the 5A nonmetals need 3 electrons. Now notice I don't go all the way down here below the stair step, because we get down into metals, and these guys are not going to have a 3 minus charge, because metals lose electrons, so the ones down here are going to have a positive charge. Okay, a little bit about naming the ions then is, if it is a metal, you're just simply going to write the name of the metal and then follow it by the word ion. So if you tell me that you're talking about sodium, I'm going to think about a sodium atom. But if you say sodium ion, then I know you're talking about a sodium with a +1 charge. Naming the ions for nonmetals is a little different because you have to tweak the name a little bit. So you are going to you're going to take the name of the nonmetal and you're going to change the ending to where it ends with "ide." So that takes a little bit of practice to learn which letters to drop and which ones to replace with "ide." But you'll get that down. So oxygen is going to turn into the oxide ion. So notice the IDE ending. Okay, but you only change the ending of the nonmetal to "ide." The metal is named just like you find it on the periodic table. Okay, what if you have a transition metal? Well, we know they're going to form positive ions because all metals form cations. Most of your transition metals and your 4A metals form 2 or more positive ions. So if we look at some of them here, this periodic table is not showing all of them, but notice chromium here can make a 2+ charge or a 3+ charge. And copper can make a 1+ charge or a 2+ charge. So what we say are the transition metals, for the most part, have what we call a variable charge. Their charge can vary, or it's not a fixed charge, where the ones back here have a fixed charge. Your 1A metals are always fixed at a +1 when they become ions. Your 2A are fixed at a 2+. Okay, so they don't change their charge, so they're not variable, they're fixed. However, the transition metals have a variable charge or a non-fixed charge. There are 4 of them, however, that have a fixed charge. So it turns out that aluminum, zinc, cadmium, and silver only make 1 ion. So if we look at this table, aluminum is always a fixed 3+, zinc and cadmium are a 2+, and silver is a +1. Now we have given on the information sheet that you're going to have stapled to every exam, you're always going to have stapled an information sheet that has the periodic table on one side and the information, some information that we've deemed to give you for the exams on the other side. So we have given you the charge on aluminum, zinc, cadmium, and silver. I still recommend, however, that you memorize these are the 4 elements that have a fixed charge. Okay, so that then that triggers in your mind to look at your information sheet and see what the charge is. So if the metal ion has more than 1 possible charge, a Roman numeral must be used in the name. So for example, iron 3+ then would be called iron 3, and actually this is a typo, I should have the word iron here. The iron, or ion I mean, iron 3 ion. So for sodium, which was a metal, we just said the sodium ion. But for iron, we can't say the iron ion because iron can have it has various charges. So you have to let the reader know what's the particular charge on iron, since it can have different charges. So something to remember is that the Roman numeral in the name is equal to the charge. Some students get that confused and they think the Roman numeral represents how many of that element there is in the formula, but that's not true. The Roman numeral is equal to the charge of the metal. So I have a copy of the information sheet I've put here just so that I can show you this. So it tells you here that the fixed charged metals. So it tells you everybody in group 1A has a +1 charge. The metals in 2A have a 2+ charge. And then aluminum, zinc, cadmium, and silver we're giving you the charges to. So those are the metals. If we're focused on the nonmetals that have a fixed charge, nonmetals in group 7A have a -1 charge. Group 6A have a -2, and Group 5A have a -3. So you don't have to memorize that whole you know, how many electrons does it take to reach an octet. We're giving you the fixed charges on the metals and the nonmetals. If it's a variable charge metal, I've got to give you the Roman numeral, because you would have no other way of knowing that for the name of the ion. All right, a couple other things I'm going to point out while I have this slide here. We talked before about the relative energies of the sublevels. So when you're asked to draw the electron configurations, this is where you find that, where you go 1s2, 2s2, 2p6, if you remember that from a previous lecture. Here's your conversions that we will have covered in recitation. So I didn't do a video on these, but we should have covered these when you were at recitation at one of your labs. Pretty soon, in a few upcoming slides, I'm going to talk about your polyatomic ions, and this is the location of the polyatomic ions. So we'll talk about these in this lecture. Part 2 of Chapter 4, we're going to get into covalent compounds or molecular compounds, and there I'm going to refer to your Greek prefixes. Okay, so here's where we have the Greek prefixes on the information sheet. So here's a learning check. What is the correct formula for each of the following? So go ahead and pause this video, see if you can do this. Now remember, I tried to warn you that a lot of students try to go directly from the name to the formula, and I don't recommend doing that. Whenever you have an ionic compound, I recommend that you first write out your ions. So copper is a capital C lowercase u, and it is a transition metal. So, and it's not the aluminum, zinc, cadmium, and silver, which means it has a variable charge. So that's why I'm giving you the Roman numeral here. So the Roman numeral is the charge. It's a +1. Nitride, so notice it's ending with "ide." So you kind of have to infer that nitride is referring to nitrogen. And nitrogen is a capital N. And you can look at your information sheet. Well, first go to your periodic table. Determine that nitrogen is in the group 5A category. So then you can look at your information sheet, and it'll tell you that your 5A nonmetals have a 3- charge. Or you can look at your periodic table and say, how many squares do I have to go over to get to the noble gases? Because the nonmetals want to gain enough electrons to get to the electron configuration of your stable noble gases. So nitrogen would have to go over 3 boxes. Okay, so I've taken the time to do the ions. I think this is a very important step. So this is a 1+. So this invisible 1 is going to become the subscript of nitrogen. It's going to stay invisible. And this 3 is going to become the subscript of copper. So we're going to end up with copper 3 and then only 1 nitrogen. So the correct answer would be 3 for that one. B says I have lead 4. So lead is capital P lowercase b. Roman numeral stands for the charge. Oxygen, oxide is coming from oxygen. It is in the 6A family. So how many electrons does it need to get to an octet? 2. So it's going to have a 2- charge. So you can do that thought process I just went through, or you can just look on your information sheet and it'll tell you your 6A nonmetals are going to have a 2- charge. Okay, now we have to do the crossing method. So this 4 is going to become the subscript of oxygen. The 2 becomes the subscript of lead. So we get Pb2O4. And I would expect a lot of students to fill in the bubble for 3 as the correct answer, but they'll get it wrong because 2 and 4 can reduce. Don't forget, cross and then reduce. So 2 and 4 can reduce down to 1 and 2. So that would be this one. So the correct answer is number 1. All right, so that's how we write the formulas for ionic compounds. I'm going to go over quickly how to do naming of ionic compounds. So here is the formula. Naming covalent compounds is different, okay? So I recommend that you kind of memorize this here setup for ionic compounds, okay? You're going to name the cation. You're going to use a Roman numeral if the metal had a variable charge. And then you're going to name the anion, okay? So parentheses are used only if the metal has a variable charge. The Roman numeral in a name equals the charge of the metal. It does not equal how many of those metals there are. So to determine the Roman numeral, you're going to draw a picture from the formula, and I'll show you what I mean by that in a second. Remember that compounds must be electrically neutral. The amount of positive charge has to sum up to the amount of negative charge. You're going to start with the charges that are fixed and then work backwards to help you figure out the charges that are variable, that you don't know. So we'll do a couple of these as an example. So name the variable charged metals. So transition metals with two different ions use Roman numerals after the name to indicate the ionic charge. So here's a couple examples. So if I had just told you, oh, go back to the room and get a bottle of iron chloride, you'd go back there and you'd be like, well, which one is it? Because iron can have a variable charge. So that is why it's important to have the Roman numeral in the name. So iron 2 chloride tells me that the charge on the iron is 2 in this case. Iron 3 chloride, I have a charge of 3 plus on the iron. Okay, so here are a couple examples. I want to sum up the rules for you one more time, just so you've seen it again. Remember that the general formula is to name the cation. If your cation had Roman numerals, put them in there. And then do the anions. Do the name of the anion. Okay. So I would do it this way. I would, step 1, name the metal. Because remember, when the cation, the name doesn't change. You spell it just like it is from the periodic table. So name the metal. And then step 2, while you're looking at your periodic table, ask yourself if you need parentheses. So write parentheses if needed. Write parentheses if metal has a variable charge. My pen is not wanting to work here. There we go. Okay, so I just usually, when I'm doing this, I name the metal and then I just put an empty set of parentheses in there if you need a Roman numeral, because I usually keep that as my last step, trying to figure out what the Roman numeral is. So step 3 then is name the non-metal. And then this part I haven't talked too much about yet. I'll build on this with the appropriate, oops, I ran out of space, appropriate ending. So right now all I've talked about is if you have an ion coming from the nonmetals, and I told you you're going to change the ending to "ide." Okay, pretty soon I'm going to teach you some different endings. And then step 4 is to draw a picture if you needed Roman numerals. So to determine the Roman numeral. So you can skip step 4 if your metal has a fixed charge. So if you didn't write down parentheses, you can just skip drawing the picture. So let me show you what I mean by drawing the picture. Actually, this won't be an example of that. The next one is. So, but let's follow these rules. The first step, name the metal. So capital C, lowercase d is cadmium. So we're going to write down cadmium. We're going to ask ourselves if we need Roman numerals. Do I need a parenthesis here? So you look at your periodic table, and cadmium is a transition metal. So you don't want to think all transition metals have a variable charge, okay? Because there's those 4 special ones which are on your information sheet. So I would memorize that aluminum, zinc, cadmium, and silver have a fixed charge. So this does not need parentheses. It has a fixed charge of 2 plus. So I get to skip. Step 2 says write parentheses if you need it, and it doesn't need it. So I'm going to skip the writing the parentheses. Step 2 is name the nonmetal with the appropriate ending. Well, my nonmetal is iodine, which I'm going to change to iodide. I'm going to change the ending to IDE because I just have iodine there. Okay, and I can skip step 4 because I didn't need Roman numerals. Okay, so for this learning check, you're actually going to need to draw the picture. So let me go ahead and do this. It wants us to name, find my marker. There we go. It wants us to name this formula. So step 1, if you're following those summary steps, write the metal. So Ti stands for titanium. Does it need parentheses? Yes, it is a transition metal, and it's not aluminum, zinc, cadmium, and silver. So it's going to need a Roman numeral. Next step, step 3, is name the nonmetal. So the nonmetal in this part is the oxygen, but I'm going to change it from oxygen to oxide. Okay, and in this example we're going to need to do a Roman numeral. So we're going to draw our picture. So I haven't taught you that, so let's go ahead and do that. To draw a picture, we make a circle. And what the circle is representing is the fact that ionic compounds need to be electrically neutral. So I'm going to put my cations and my anions in this circle, and their charges better sum up to 0. So really what I do in my head, I don't usually draw this line, but I cut my circle in half, and I keep my cations on the left and my anions on the right. So the reason I do that, and I didn't stress this point, but when you're writing an ionic compound, you always write the cation first. And in your formula, it'll always be followed then by the anion. So you won't see ionic compounds where you have the anion written before the cation. Okay, so here's my picture. I've got my circle. And I look at the formula, and it shows me that there's only one titanium. So I'm going to put the one titanium in here. And then looking at my formula, I can see 2 oxygens. Now the whole purpose for doing this circle is to try to figure out the charge on titanium, because that's going to be the Roman numeral. So when you have a metal with a variable charge, you're always going to be able to, or just all the time, you're going to be able to figure out the charge on the anion. So the right side of this circle, whatever element you're writing there, we should be able to figure out the charge somehow. Well, oxygen is in the 6A family. So that means it's going to make a charge of 2 minus. Okay, and here's where we have to do some math. What is the total amount of negative charge? Well, a 2 minus and a 2 minus is minus 4. So since my charges have to be equal, that means I must have to have a positive 4 here, because positive 4 will exactly balance out the negative 4. And then I have to say to myself, okay, my cations are bringing in a total of positive 4, and I only have 1 titanium. So that positive 4 must be the charge on the titanium. If I had had 2 titaniums, I'd have to divide that positive 4 into 2, and each one would be a 2 plus. But in this case, I just have 1 titanium, so it will be 4. If you need to refresh up on your Roman numerals, you'll want to do that. So here is another learning check. I want you to write the formula and name the compounds of the following ions. So let me just pick one for you to do real quick. Down here I have this little memory reminder. To write the formulas, cross the charges, and don't forget to reduce. To name them, name the cation, use Roman numerals if you need to, and then name the anion. So let's go ahead and do one of them. Let's do this guy right here. So SN stands for tin. Oh wait, let's do the formula first. So I'm going to put down my SN. How many tins do I need? Well, I look at the charge on bromine, and it's a -1, so I only need 1 tin. So then I write down bromine. How many bromines do I need? So I look at the charge on the tin, and that's a 2 plus, so I'm going to need 2 of those. Okay, crossing. Can I reduce this? No, a 1 and a 2 can't reduce. So that's how you write the formula. To name it, we write it out. So tin. Tin has a variable charge, so I'm going to write the charge in the Roman numerals. I don't have to draw a picture for this one because it's showing me the charge. It's a 2 plus. And then bromine is going to change to bromide. Okay, so you'll want to, for practice, fill in all the squares in this table, and the next slide I have all of the answers for you. Okay, one more little concept before we finish up ionic compounds. Polyatomic ions. So let's just look at this word for a second here. The prefix poly means many, and the atomic means atoms. So polyatomic means many atoms, and the word ions means it has a charge. So a polyatomic ion is a group of atoms that has an overall ionic charge. And here are some examples of a couple polyatomic ions. Do you notice that this first one has one nitrogen and 4 hydrogens? So that's my grouping. That's my polyatomic. And then it has a +1. So an NH4 with a +1 is called an ammonium ion. Here I have a grouping of 1 nitrogen and 3 oxygens, and it has a -1 charge, and that's called the nitrate. If you look at your information sheet, there's a category there almost in the middle that's titled polyatomic ions. And we are giving you several polyatomic ions, okay? And these here are a few of them. Here are some compounds that contain polyatomic ions. So it's going to be pretty important that you can look at a formula and quickly say to yourself, this one contains a polyatomic ion, okay? Because if it doesn't contain a polyatomic ion, you're going to end the naming with IDE, like we did in the previous examples. These ones, however, contain a polyatomic ion, so they're going to end differently, so you have to be careful about that. So here they're showing Windex, which is ammonia dissolved in the solution, and when ammonia dissolves in a water solution, you end up getting this ammonium hydroxide. So when you look at this, do you agree that we have some polyatomic ions? Okay. So the way you're going to know you have polyatomic ions is if you have more than 2 different types of atoms. If the last example we were working on, let me go up here to the side, was the titanium oxide. That was the last one we wrote a name on. And do you see how there's just titanium and oxygen? It does not contain a polyatomic ion if you just have 2 elements. Here I've got nitrogen, hydrogen, oxygen, and some hydrogen. So we definitely have a polyatomic ion because there's more than 2. Over here I see calcium, I see sulfur, and I see oxygen. So 3 types of atoms. So this contains a polyatomic ion. Same thing here, sodium, nitrogen, and oxygen. It contains a polyatomic ion. What we've done down here is they've actually pulled the polyatomic ions together, separated them. So the ammonium hydroxide, they're showing the ammonium here. There's ammonium, here's the hydroxide, an oxygen and a hydrogen with its -1 charge. So polyatomic, many atoms bonded together, and then they have this overall charge to them. Here's calcium sulfate. The calcium is just an atom, but the sulfate is a polyatomic, and it's an ion. And I said atom for calcium, but it's an ion because it has a charge. And here's sodium nitrate. So the names of some common polyatomic ions. We are giving you several on your information sheet, and we're going to stick to those ones. And if you notice, most of them are going to end with the ending 8. There are a couple exceptions. I actually recommend that you memorize the 2 that are exceptions. So ammonium, the NH4+, and hydroxide. So both of the 2 in this very first one are the exceptions. So I really recommend that you memorize these 2. Oops. Okay. All the other ones are going to end with 8. And the ending of 8 is going to trigger in your mind, polyatomic ion. I'm going to flip over my periodic table to my information sheet, and there's all my polyatomic ions. But when you see hydroxide, hydroxide actually ends with IDE, which was our ending to the monatomic ions, the nonmetals on the periodic table. So hydroxide throws students off sometimes. That's why I recommend memorizing it. Okay, so on your information sheet, we're going to give you the polyatomic ions that end with 8. But there's a trick that I'm going to need you to learn, which is, what do you do if your polyatomic ion ends with "ite" instead of 8? And here is the trick, which I actually tell you on the information sheet. If you see your polyatomic ion with 1 less oxygen, then that is going to change the ending from an 8 to an "ite." Okay? So ITE means take off 1 oxygen from the polyatomic ions that we're giving you on the information sheet. So notice here is nitrate, which we give you on the information sheet. But I might ask you for the name of this one. And you would say, okay, well, NO3- is nitrate, so NO2-, 1 oxygen less, I'm going to erase the 8 and turn it into "ite." Notice when you take off one of the oxygens, the charge doesn't change. Okay, so you remove the oxygens but keep the charge the same when you're doing that. Another changing to the more common 8 polyatomic ions is what happens if you add a hydrogen ion. So when you add a hydrogen, you're going to attach the prefix hydrogen or the prefix bi. Okay, so here's a couple examples. Carbonate is the CO3, actually carbonate is CO3 2-. So CO3 2- is carbonate. When you add a hydrogen ion to that, the plus charge balances out one of these negative charges, and we end up with just a -1. So we actually give you hydrogen carbonate on your information sheet, which is also called bicarbonate, and we're just going to stick to that one. So you won't have to change the naming when you add hydrogen to the polyatomic ions, but you will be expected to change the 8 to "ite." Okay. So here's a learning check. Before you pause the video to give these a try, I just want to sum up a couple things, okay? Remember the formula for doing an ionic compound. So the rules for doing an ionic compound are name the metal, use parentheses if you need to, and name the non-metal. But remember, when you're naming that anion, you got to be careful about the endings. So let's sum up real quick. Let me grab my pen again. Let's go sum up my endings. So endings for nonmetals. For anions. You have three choices. You're going to use the ending "ide" if it is a monatomic anion, meaning there's just one type of atom. So from the periodic table, if it's iodide or bromide, then you're going to end it with "ide." Or it's going to end with either "ite" or "ate." So you're going to use "ite" or "ate if it's a polyatomic ion. Okay. The other thing I want to summarize is when you need the Roman numerals. Okay, so you're going to always put the Roman numerals. So let's see, Roman numeral except. Okay, so Roman numeral if it has a variable charge. No Roman numeral if it has a fixed charge. So the fixed charge ones are metals that are in the 1A family, metals in the 2A family, or aluminum, zinc, cadmium, and silver. All of these metals are not going to use parentheses with the Roman numeral. All the other metals will. Okay, so let's give this a try. We have magnesium, so we write down that name. Name the metal. Ask yourself, do I need parentheses? So you find magnesium on the periodic table, and it is in group 2A. So it has a fixed charge, so I do not need parentheses. So I'm going to move on. I go to name my anion, and I can see it's a polyatomic ion. So it's going to end with either "ite" or "ate." Okay, so I look on my information sheet and I can see NO3 is on there, so it's just going to be nitrate. The second one, Cu, is copper. Is copper in 1A family, 2A family, or one of these special four? No, it's not, so it's going to need parentheses. I come back to the Roman numeral last, so I just put the parentheses there to remind me I have to come back to that. And then I look over to my anion and I can see it's a polyatomic anion because I see chlorine and oxygen there. There's more than one. So I look on my information sheet and that is the chlorate ion. Okay, here I need to figure out the Roman numeral. So the way I do that is I do the circle method. And I look then at my formula. So that's where a lot of students get stumped. They know they need to do the circle method, so I see them doing that on the test, but then they don't know where to go from here. So remember, once you've drawn that circle, bring your eyes back to the formula. Okay, so let's go over here and look at the formula. I've got 1 copper and 2 chlorate ions. Okay, if you have more than one polyatomic ion, you end up putting parentheses around that polyatomic ion. So the subscript out here tells you how many chlorates we have. So there's 1 copper and 2 chlorates. Now remember, I told you that when you're doing the circle method, you do it because we're trying to figure out the charge on the metal. So there's going to always be some way of figuring out the charge on the anion. If it is a monatomic anion, so there's just one type of atom here, you're going to look on your periodic table and see what group number it is. But since this is a polyatomic ion, you're going to look at your information sheet and it'll tell you. And it tells you that chlorate is a -1 charge. So now we can do our math. My anions are bringing in a total of -2 charge, so my cations need to bring in a +2. And I only have 1 copper, so that 1 copper must be carrying that whole +2 charge. I don't have to divide that positive charge up amongst more cations. So that's the copper 2 chlorate. Moving on to part C, Pb stands for lead. And lead is not in the 1A, 2A, or these four, so it does need parentheses. I'm now going to name my anion, and when I look over here, I just have oxygen. It's not a polyatomic, so how's it going to end? The oxygen is going to change to oxide. Okay, but I do need to do a circle because lead has a variable charge. I have got 1 lead and 2 oxygens. I always have some means of figuring out the charge on the anion, and since it's in the 6A family, all 6A nonmetals become 2-, so that gives me a -4 coming in from the anion side. So my cations need to bring in a +4. And I only have one lead, so it is going to be a 4+. So that is my Roman numeral, lead 4 oxide. Okay, the last one, Ba stands for barium. Barium is in the 2A family, so I do not need Roman parentheses or Roman numerals. Move on to the second part. This is a polyatomic ion. So I look at my polyatomic sheet to see what it's named. Well, it does not have PO4 on there, or it doesn't have PO3 on there. It does have PO4, however, and your information sheet tells you that PO4 is called phosphate. So you need to figure out what you're going to call this PO3. Well, notice it is 1 oxygen less. So the 8 is going to turn into ite. So this is barium phosphate. Okay. So here is a learning check. I want to do one of them for us. Let's go ahead and do the calcium carbonate. Let's do this box right here. I'm going to do it off to the side for a second, though. So up here, calcium with its 2+, and the carbonate with its 2-. I picked this one on purpose because a lot of people forget that second step. So we're just going to cross. So we're going to bring the 2's down. So we would have calcium, I need 2 of those. Carbonate, well, I need 2 of those. But remember to reduce. 2 and 2 can reduce down to 1 and 1. So you're going to end up just with 1 calcium and 1 carbonate. Okay. If we were doing the second one, how many calciums do I need? So I look at the charge on my anion, and that's 3. And then I write down my anion, PO4, and I ask myself how many PO4s do I need? So I look at the charge on calcium, and I need 2. Now, if I just put the 2 down here, I'd have a problem, right? That's going to look like 42 oxygens. So remember, put parentheses around your polyatomic ion if you have more than one of them. If you only have one, like over here, the carbonate, you don't need parentheses around it. I would never dock you points. Some students like to keep parentheses around that. I understand what you're doing. I would not take off points for that. But when you're doing your homework, the software is going to be picky about little things like that. Okay, so I have the answers for you on the next slide.